Good day, my name is Vermaas Bissett and I will be presenting this video on the modeling of cable terminations with finite element analysis by making use of the QuickField program. The importance and reasons for termination modeling. There are many reasons why modeling of cable terminations are important. One could have the following summary. It is a critical component of power systems at all voltage levels. Number two, there is currently evidence in the industry of high failure rates, especially at the medium voltage level. It is a specialized and complicated domain. Many defects due to poor workmanship can be simulated by making use of finite element analysis. Number five, it will increase our understanding of a behavior and root cause of failures. Number six, support factory and on-site commissioning test. There are many international and national standards that prescribe certain voltage levels when it comes to on-site commissioning. By making use of suitable models, one could have a better understanding on the specified voltages that are required. Number seven, it will also improve the quality assurance, especially if modeling can be incorporated into the training curriculum for cable terminations. And then most importantly, it will have an integrated approach whereby the theory, the practice and the modeling of electrical engineering will be combined or integrated to add additional value. Why finite element analysis? The underneath picture represents the partial discharge models that are currently available within the industry. On my far left-hand side is the capacitor model, or the traditional ABC model that is most common for simulating partial discharge within materials. One also gets induced charge models and plasma models. But a very attractive method to simulate cable terminations is finite element analysis, especially with the electrostatic capabilities of finite element analysis. Why is it so attractive? It can increase our engineering understanding of this domain. It is excellent for visualizing the model and the component that is under evaluation, and one can relate the electric field strength to the partial discharge. The overview of the presentation and demonstration. In this video, I will explain and demonstrate with QuickField the critical stress area at the triple point. I will further represent three QuickField models. The first one will be the termination defect that is most commonly found in the industry, which is called the ring cut at the triple point, and this will be done with an axisymmetric model. We will also have a look at a defect-free termination with all the subcomponents, and then we will also have a third model that will represent the cable as prepared but prior to adapting any of the components of a termination, and this will be done in a 3D extrusion model. Then lastly, there will be a comparison between the calculated values and the simulated values of electric field strength at the triple point. If one creates a model for cable termination, a defect-free model, it is important to follow the following criteria. A precise dimension should be followed at all time when referring to the instruction manual, and the material detail for all the subcomponents must be known. It is also important to have a good understanding of all the subcomponents, like the stress relief mastic, stress control tube, and the anti-track tube. Furthermore, when one builds the 3D model, there should be a clear understanding of all the dimensions that are applicable. When building the ring cut defect and the defect-free termination, one will have a look at the constructed model within the QuickField program, and I will also refer back to this sketch just to make it very clear where all the subcomponents of the cable termination are located. In this video, with all the modeling and simulation, a single core XLPE cable will be used. This is the cable that was used with the dimensions. In short, this is the insulation or the XLPE, the semiconductive layer, the copper tape and the sheath. In the video, the triple point will be discussed, which is basically this point where the semiconductive layer, the XLP insulation and the air comes together. So the triple point is the circumferential area around the cable, which is considered to be the critical point. In order to prepare the cable for the termination, good workmanship is required in this area, as well as the correct tools, as well as the importance to follow the instruction manual in terms of dimensions. The following section of a video will focus on modeling a defect-free cable termination as far as possible. We will construct an 11 kV cable termination by making use of an XLPE cable. We will use the detail as presented earlier on by making use of the various components that form the cable termination. This sketch can be used as a reference where the various parts of the cable and the termination are indicated. For completeness sake, we will quickly indicate where the cable and the cable termination components are. First of all, we will start off with the insulation, then the semiconductive part, as well as the ground part or the copper tape that is part of the cable, as well as the outer sheath or shield. Then inside the cable termination, the components that have been used is various mastics. The first one is the one that you will find at the triple point where the semiconductive part, the XLPE insulation and the air comes around. So this mastic is very important. Secondly, the stress control tube. Then there is another piece of mastic tape that is applied, and then at the end you will have anti-tracking tube across the entire termination. This model has been built already and the mesh has been created. The ground voltage is clearly indicated in this area, which is the copper tape. The nice thing about modeling the termination is selecting the various voltage levels. So the phase to ground voltage for this termination will be 6,350 volts. So this will be our first simulation, just to see if the model is working. The important factor to measure is the electric field strength. As you know, air breaks down at around 3 kV kV per millimeter. So as soon as you reach those levels, it will become critical for the performance of a cable termination. One can now zoom in and select the field strength, which will be our primary indicator to monitor during the simulation. If I zoom into the critical area, which is the triple point, the field strength is less than 3. Currently it's standing at 2.53 kV per millimeter, which indicates that the workmanship and the way the termination has been assembled is good. One can now continue to increase the voltage. The next one will be at 12.7 kV. And this is also the typical values that the test engineer will use when he is commissioning the cable termination. Once again, there is a correlation between the applied voltage and electric field strength, but it is important for the density around that area and how that will change with the increase in voltage. Once again, we select the electric field strength. We apply the legend and we zoom into the critical area. So already at twice the rated voltage, one could see that there is an increase in the electric field strength above 5, although it is restricted to a very small area. The third test point will be at 19 kV. Typically, if one considers international standards, depending the country and the type of standard, the test voltage can go up to 4 or even 6 times the rated voltage. So let us look at the field distribution at 3 times the rated voltage. One could see once again it is in the critical area. It is more than 7 kV per millimeter, but it is restricted to a very small area. So the benefit of modeling cable terminations with finite element analysis is to also prove that the modeling relates to the applied test voltage. The next section of the video will focus on how we can use QuickField to simulate defects within cable terminations. We will use exactly the same model as the previous section, a typical 11 kV cable, but for this part we will create a defect within the critical area. This is the triple point as previously explained. So we will create a defect around the ring cut area, which is in the circumferential area around the semiconductive insulation area. We have created an insert of 1 millimeter deep and 1 millimeter wide. So this defect is across the entire cable area. This defect is very common. It can occur by not making use of the correct tools. It can also occur if it is due to poor workmanship, or even if the various components of a cable termination is not applied in accordance with the instruction manual of a termination. So this all could lead to defects. So this section will focus on how we can use QuickField to simulate one common defect type, which is the ring cut defect. Once again, we will create the model. We will apply all the various parameters. We will create the mesh. The ground is still the same. In this instance, we will start off once again with a voltage of 6.35 kV. We will run the simulation and we will look at the results in the critical area. Once again, we are interested in the electric field strength in that area. So the electric field strength is less than 2.5 kV per millimeter, which is not that high, but it is quite extensive in this area across the entire 1 millimeter deep insert into the XLPE insulation. So with time to come, this void that is created will be across a high stress area, and this will start to deteriorate the insulation due to partial discharge, which is the effect of the electric field strength. It is due to chemical reaction. It's due to the electrical phenomena in that area. And with time to come, this area will start to grow. The next voltage will be 12.7 kV. Just for comparison purposes, in relation to the previous section, it's focused on a defect-free termination. There is obviously a great correlation between the voltage applied versus the electric field strength, which can be seen in this model as well as in the previous model. Once again, the electric field strength is far above 3 kV, so breakdown in air will start to occur in this area, and it is quite significantly large area. Once again, we will go up to 3 times the rated voltage, which is 19 kV. So even at the rated voltage of 6.3 kV, the electric field strength is in the order of just below, which is already enough for discharge to occur. One could see at 3 times the rated voltage, the electric field strength is almost 7.5 kV per millimeter, which is quite significant. Although it is not much higher than the defect-free termination, the area is of importance. The next section of this video will focus on the electric field strength at the end of a cable that was prepared in accordance with the instruction manual, meaning that the semiconductor and all the necessary layers have been prepared and the cable is ready for the termination to be applied. There are 2 reasons why we would like to look at the electric field strength in the critical area. We all know from literature and from practical investigations that the semiconductive or the triple point area, where the semiconductive layer, the insulation and the air comes together, that one is expected to find high discharge and high electrical strength in those areas. But we would like to visualize it and we would like to model the values. And then secondly, we would like to compare the simulated values to the mathematically calculated values. We will use 3 different voltage set points where we will change the applied voltage. We will use the same cable dimensions as previously, and in particular we will use the following radii. The inner radius of the conductor will be 4.9, the inner radius of the air is 11.2, and the outer radius of the air is 12.2. So we are interested in the electric field strength in the area 1 millimeter above the XLPE insulation. It is also possible to calculate the electrical field strength in this vicinity by making use of the following equations, where one can use the following criteria in order to calculate the voltage at the surface, the electric field strength inside the insulation, but in our case we are interested in the electric field strength at the surface 1 millimeter above the insulation. All these details can be found in the book Some Faults on MV Cable Accessories. Then finally, we will compare the calculated values at the 4 different voltage points. We will calculate the electric field strength and we will compare it to the simulated field strength. This model will be built by making use of the 3D extrusion model class, and like the previous sections, the problem type remains electrostatic. Only a quarter of the cable will be built, and this allows for faster simulations and also for easy access to the internal parts of the cable. As previously, the parts of the cable as presented in this model are the conductor, the insulation, the semiconductive layer, the copper tape, the inner bedding, the sheath, and then very important, it is also required to create the air around the cable in order to finalize the mesh created for the model. Once the model has been built in the 2D view plane, one must now apply the various block levels to create the third dimension. The conductor will go from 0 to 80, and you have to insert these levels under the block details. The insulation will be from 0 to 60, and the remaining portion from 60 to 80 is required for the air. Likewise, the semiconductive layer is from 0 to 50, and the air is from 50 to 80. The copper tape, 0 to 40, and 40 to 80 to make provision for the air. The inner bedding, 0 to 20, and 20 to 80. The sheave is 0 to 10 and 10 to 80. The air gap is from 0 to 80. It should be noted that the dimensions here is not 100% in accordance with the cable termination due to the sizing, and for demonstration purposes, as we are only interested in the triple point for viewing. Once the various levels have been inserted, you can now go to the 3D model to visualize your cable, and it is best to hide the air so that you can see the cable as prepared in a better way. So once again, to confirm your model, that is the conductor, that is the insulation, that is the semiconductive part, that is the copper tape, the inner bedding, and then the outer sheath. So the model appears to be correct, and remember to also include the air in order to allow for successful simulation. For the first simulation point, we will select a voltage of 11 kV. Let us run the modulation. So we are interested in the electric field strength in this area, the semiconductive layer and the insulation right here. That is the point of interest. For better visualization, let us hide the air. Let us zoom into the point of interest. And let us select the electric field strength. So we are interested in the electric field strength in this area. The semiconductive material is about 1 millimeter thick. So in order for us to look at the values 1 millimeter above the insulation, I will, for consistency's sake, select the point on this outer peripheral area. So the electric field strength is about 2.06. So we can insert that. We can insert that in the simulated values as the first data point under 11 kV. Let us run the second simulation at 22 kV. Once again, let's zoom into this particular area of interest. We will select E and we will measure the field strength. It appears to be 4.3 kV. We can insert that. As the second data point. One can also, for better visualization, select the vector plot, which can clearly indicate that the highest field strength is towards the semiconductive layer, which is about 1 millimeter above the insulation. Let us simulate the third data point, which is 33 kV. Let us run the simulation. It is also important to note that the simulated voltage selection 11, 22, 33 and 44 is typically in accordance with test standards for cable commissioning. This is now the third data point at 33 kV. Although one expects an increase in electric strength in proportion to the selected voltage, it is best to also simulate it. The value is about 6.5 kV per millimeter. And the fourth and last data point will be at 44 kV. Once again, For interesting sake, you can select the vector plot, but clearly indicates by means of the arrow that the electric field strength is strongest in this area. So let us simulate the fourth point. The value appears to be 8.6 kV. So this was the simulation or the modeling of 4 different data points to obtain simulated values for the electric field strength in this area. Let us see how the calculated and simulated values compare. As previously presented, by making use of the equations, one can calculate the electric field strength by the various radii, and we are interested in that field strength values at 1 millimeter above or outside the insulation. The 4 values as calculated is 2.47, 4.93, 7.4 and 9.87. It compares with the simulated values of 2.06, 4.3, 6.5 and 8.6. So although the modeled or simulated values is slightly below the calculated values, there is great correlation. Both follows as expected a linear increase in the electric stress at the 4 different voltage test points. So this proves from a theory perspective and from a simulated perspective that the triple point is indeed the area which is exposed to the highest electrical stress. Some final observations. QuickField was successfully used to model and build cable terminations, both in the axisymmetric plane and also in the 3D extrusion plane. The second one, evaluate electrical field strength in relation to variations and applied voltages. Variations means the way that the model is constructed by making use of the various components of the cable termination, and the applied voltage is the rated voltage up to 4 times the rated voltage. QuickField was also used to model defects within cable terminations and also to model the prepared cable end before the termination components were applied. It was confirmed that the high stress area in the termination is indeed the triple point, Number 5, importance of dimensions and material details. When constructing the defect-free termination, it is absolutely critical to follow the dimensions precisely and also to obtain all the material details, especially the permittivity of the components. There is indeed a good correlation between the theory, the practice, and the modeling. If one goes back to the defect that was simulated, the 1 by 1 millimeter defect with a high electrical stress in this area, with time to come, over many years, depending on the magnitude of the error, the partial discharge will start to deteriorate the insulation and the semiconductive layer, and it will move in this direction to eventually cause a flashover between the ground or the copper tape and the conductor. So the fault in most cases happens in this area. Some conclusions. Excellent correlation was found between the calculated and simulated values for the electric field intensity. It was visually shown and calculated and modeled, but the triple point is the most critical area. And the finite element analysis simulation with QuickField adds value in the following areas: the application of termination to the end user, the engineer to understand and comprehend the practice and the theory, and QuickField can also add value for designers of cable terminations. I would like to thank QuickField for making the program available for research on cable terminations, and I would also like to thank all the viewers that will make the time to watch this video. Thank you.